Bending stresses in beams. Introduction. When a flexure member or beam is subjected to external loading, each and every section of it experiences bending moment and shear force. Under combined effect of these bending moments and shear forces, beam will start bending. A resistance or stress will be developed at each section to check deformation or bending. Upper layers will induce bending compressive stresses and bottom layers will induce bending tensile stresses. For a simply supported beam, the maximum bending moment is obtained at center of span and maximum shear force is obtained at supports. Bending moment induces bending stresses at every section and shear force develops shearing stresses at every section. We are concerned with maximum stresses due to bending moment and shear force at most critical sections. If a section is strong enough to bear maximum stresses at most critical sections, will obviously be safe at all sections having lesser values of these stresses. The strength of beam is calculated in terms of moment of resistance. Moment of resistance is governed by a factor named section modulus. Distribution of bending stresses and strains at a cross section. The stresses developed due to bending are compressive and tensile in nature and are called respectively bending compressive stresses and bending tensile stresses. The top fibers experience compression and bottom fibers experience tension, but there is a layer which remains at original length and does not experience tension or compression. This layer is known as neutral layer. The intersection of neutral layer with cross-section gives a line known as neutral axis. As we go towards top, with respect to neutral axis, the compression in layers will increase, correspondingly bending compressive stresses will also increase linearly. The topmost layer will have maximum compressive stresses due to bending. As we go towards bottom, with respect to neutral axis, the tension in layers will increase, correspondingly bending tensile stresses will also increase linearly. The bottommost layer will have maximum tensile stresses due to bending. Assumptions for the theory of pure bending. 1. The beam is subjected to pure bending and is therefore free from the shear force. 2. The material of the beam is homogeneous and isotropic. Isotropic means having the same elastic properties in all directions. 3. Each longitudinal fiber is free to extend or contract independently. 4. The value of the Young's modulus is the same for the beam material in tension as well as compression. 5. A transverse section of the beam which is a plane before bending will remain a plane after bending. 6. The elastic limit is not exceeded. 7. The resultant pull or thrust on a transverse section of the beam is 0. 8. The radius of curvature of the deflected beam is very large compared with the dimensions of the cross-section of the beam. 9. The transverse section of the beam is symmetrical about an axis passing through the centroid of the section and parallel to the plane of bending. Theory of simple bending. The layer AC is shortened to A1C1, hence it is subjected to compressive stress. The layer BD is elongated to B1D1. Hence it is subjected to tensile stresses. Hence the amount of shortening decreases from the top layer towards bottom and the amount of elongation decreases from the bottom layer towards top. Therefore there is a layer EF in between which neither elongates nor shortens. This layer is called neutral layer. The value of bending strain and bending stresses increases with distance from neutral axis. The extreme distant fibers from neutral axis have maximum values of bending stresses, named as extreme bending compressive stresses and extreme bending tensile stresses, respectively.
For complete course and step-by-step illustration, please subscribe full course on Structural Analysis and Design app. Also subscribe YouTube channel Maatrixx Digital Solutions. Thanks for watching.